This is the PhET simulation using a converging lens, or sometimes this is called a convex lens. And this is how the thing starts when you load it up. You have an object that is this pencil in a picture frame, and the image that's produced on the other side of the lens. And so you can grab the object and move it around and see that the image changes as a result of doing so. And there's a few representations you can do here. You can have no rays and just see how one produces the other in a lens. You can have what the default is, which are these marginal rays, which are rays that go from the top of the pencil through the top, middle, and bottom of the lens. You can have something called principal rays, which in other physics courses that focus more on the numbers and the math, you learn something called ray tracing, and so these are considered the three principal rays, and you'll notice they don't always actually pass through the lens, so for our purposes probably not super helpful. Or you can have many rays to emphasize that off of any point there's light going in all directions, and it's only the fraction of the light that passes through the lens that produces the image. I'm going to go back to the marginal rays. I think there's a reason they leave this as a default. You can alter the radius of curvature of the lens, so you can make it fatter or narrower, and doing so actually changes the position of the image that you produce by changing the focal point of the lens. And you can see the little focal point here with the X on either side of the lens. You can change the refractive index, so make the lens out of a different kind of simulated glass and change the diameter and such. I'm not going to worry about those for here, but I am going to change the. Let's see. I thought in here somewhere there was a single light source. Perhaps not. Maybe I'm thinking of a different simulation. Anyhow, all right, let's explore what happens specifically when you change the object distance. So right here I have an object distance and a certain image distance, and when I move the object distance so that the object distance from the object to the lens is a smaller distance, you'll notice that in this system the image distance gets larger. And if I move it closer and closer and closer, the image distance is getting larger and larger and larger. It's going to go off the screen here in a bit, but that's okay. I just wanted to point out what happens when you get here to the focal point of the lens. You actually no longer produce an image, but then if you get closer to the lens, you can get a virtual image, and I'll turn on the virtual image tracing here. All of these rays are where the light's actually going, but if you're a viewer over here on the right side of the lens, the yellow rays show where the rays appear to have come from, and so this is the physics arrangement of using a magnifying glass to look at some text close up, and you can magnify something quite a lot depending on where you place the actual object relative to the focal point of the lens. For the purposes of the lab question, if you will, it's asked us to find the relationship between the object distance and the image distance. I'm going to take a little data in my Google Sheet data table over here. So I'm just going to start with a relatively large object distance and turn on a virtual ruler to allow me to measure things. So if I measure here, I wonder if it lets me turn this around. Probably not. Okay, so from the center of the pencil to the center of here, I'm going to estimate that's 186 centimeters. And if I do so, move my ruler to the other side, from the center of the lens to the point where I'm getting a pencil is about 26 centimeters. If I move my object distance in a little bit, now I have, say, 170 centimeters on the object side. And now I have 135 centimeters on the image side, it appears. Do this a little bit more. My object is now about 152 centimeters. And my image is about 150 centimeters. Now, about 136 centimeters on the object side. And on the image side, 100, maybe 72 centimeters. Let's get one more, because it said, well, somewhere I thought it said at least 5 data points. So go with that. Let's push it to the edge of the screen here. So on the object side, I think that's about 122 centimeters. And on the image side, that is right about 200 centimeters. So you can see that the data confirms what you can see just visually at the beginning. As you decrease the object distance, the image distance gets larger, or as you increase the object distance, the image distance gets smaller. And mathematically, this is known as an inverse relationship.